During the second module, we are dealing with nuclear physics, and in this 8th video, we will explain how to transform a part of the nuclear binding energy into heat by nuclear fission. After viewing this video, you will know how the nuclear fission mechanism works and its necessary conditions. A very important application of nuclear physics is the transformation of nuclear binding energy into thermal and then electrical energy by the fission mechanism. Low-energy neutrons can penetrate inside the nucleus since they are not subject to Coulomb repulsion. This way they increase the nuclear mass, and the excited nucleus may break up into two daughter nuclei of smaller mass. This fragmentation of a heavy nucleus into two medium mass fragments plus accessory products is called nuclear fission. The alpha decay, which we have discussed in video 2.4, is an extreme example of a very asymmetric spontaneous fission. But more important is the fission induced by the absorption of a neutron. Nuclear fission stays in the domain of a heavy mother nuclei, and this is due to the shape of the binding energy per nucleon as a function of the mass number A, which we have shown in video 2.1. Beyond the iron group, it decreases steadily, such that binding energy can be gained by splitting a heavy nucleus into two nuclei in a more or less symmetric way. Thus, a less tightly bound heavy nucleus can gain binding energy by splitting into two lighter, more tightly bound ones. As an example, the binding energy per nucleon is minus 7.5 MeV for uranium-235 and minus 8.4 MeV on average for the two daughter nuclei. The energy released by fission is typically 0.9 MeV per nucleon. 1 gram of uranium-235 contains about 3 times 10 to the 21 nuclei. The complete fission of all of these nuclei would release the impressive energy of 10 to the 11 joules, about 1 megawatt a day, if we ignore all the efficiency involved. To give you an idea, for comparison, burning 1 ton of coal yields about 0.36 megawatt a day, if again we ignore efficiencies. Thus, 1 gram of uranium-235 contains as much nuclear energy as 3 tons of coal contain in chemical energy. We can understand the nuclear fission qualitatively and quantitatively using the liquid drop model of the nucleus, which we have introduced in video 2.3. Let's first look at the process qualitatively. The liquid drop model presumes a spherical shape of the nucleus, but for a heavy nucleus, a small external perturbation, like for instance an incident neutron, can produce surface waves leading to a change in shape. The drop may thus extend into a spheroidal shape, and if this perturbation is small enough, the nucleus will be left excited and just return to its ground state by emitting a photon. This process is called radiative neutron capture. If, on the contrary, the perturbation is large, Coulomb repulsion along the axis of the spheroid can split the drop into two droplets by what is called induced fission. Now let us calculate under which condition this may happen. A sphere radius r will turn into a spheroid of a constant volume because of the incompressibility of nuclear matter. We denote its alpha-axis by A and B, which is equal to C, and in terms of a small deformation epsilon, they transform into B minus epsilon and A plus epsilon. For the binding energy, the volume terms stay constant, but the surface and Coulomb energy are different. The deformation increases the surface energy but decreases the Coulomb term. So the gain or loss in binding energy will depend on the relative importance of these two terms. If the difference is greater than 0, the spherical nucleus is more tightly bound and thus stable against the small perturbation. If, on the contrary, delta is less than 0, the spherical nucleus is less tightly bound and can undergo fission. Putting in the typical values for the coefficients A2 and A3, one obtains stability if the ratio between Z square and A is less than 47. There are small quantum corrections to this classical approach, which, however, does not change the conclusion. We expect, on the contrary, the nuclei with Z square greater than 47A are highly unstable against a small perturbation and then can be easily induced to fission. Heavy nuclei have Z less than half A, so the condition Z square less than 47A is satisfied. The spherical shape corresponds to the maximum binding energy, but even in that case, fission can be energetically favorable if the sum of binding energies of the daughter nuclei is favorable with respect to the mother nucleus. Let us calculate this case for a symmetric fission, assuming a spherical daughter nuclei for simplicity. A and Z of the parent nucleus must thus be even. We again ignore quantum terms of the Bethe-Weizsäcker formula. The energy difference is denoted by delta. With typical coefficients, we obtain delta equal to 0.27 A at the power 2/3, which times minus 16.5 plus the ratio Z square over A. Thus, for Z square less than 16.5 A, the two daughter nuclei are more tightly bound than the mother nucleus. We thus see that for the region Z square between 16.5A and 47A, the spherical shape itself may be stable against fission, but it remains energetically favorable for the parent nucleus to split into two smaller ones when it is sufficiently perturbed. Beyond that zone, even a minor perturbation by a thermal neutron, for instance, will suffice to cause fission. Let us consider uranium isotopes as an example. Uranium-238 is an even nucleus and thus more tightly bound than uranium-235, which is odd-even. We'll thus need a smaller perturbation to induce fission in uranium-235. The activation energy is about 5 MeV for uranium-235 and 6 MeV for uranium-238. When capturing a neutron, uranium-235 becomes an even nucleus. This transformation releases about 6.5 MeV of binding energy, which is sufficient to activate its fission. For uranium-238, a neutron capture changes the nucleus to a less tightly bound odd-even one. This will be a less exothermal process. It releases only 4.8 MeV out of the necessary 6 MeV, so additional 1.2 MeV per neutron must be provided to induce fission. The fragments are often rather asymmetric. One observes a grouping of the daughter nuclei around mass number 95 and 140, as shown in this picture, for a reason which we have not yet understood. The picture here in fact shows the mass spectrum of daughter nuclei from the fission of uranium-233, uranium-235, plutonium-239, as well as a mixture. The mass spectra are similar. After the fission process, the daughter nuclei are often in an excited state and they turn into stable isotope by neutron emission. Neutrons are thus abundant among the fission products. They can cause a chain reaction of nuclear fission processes. Uranium-235 produces on average 2.5 neutrons per fission. These neutrons can in turn induce new fission reaction and so forth. To see if a chain reaction can be maintained, we consider the ratio K of the number of neutrons produced in step n plus 1 to the one produced in step n of the chain. If K is less than 1, there are not enough neutrons to sustain a chain reaction and the process will stop itself. If K is equal to 1 or around 1, there are just enough neutrons to maintain a chain reaction with a constant number of fissions at each step. This is the ideal situation for a nuclear fission reactor. If K is bigger than 1, more and more neutrons will be produced at each stage, thus leading to an exponential growth of the number of fission reactions. And this is the situation which is searched for the production of nuclear weapons. In the next video, we will talk about how to use the fission process in nuclear power plants.